We will start in a couple of minutes. So I will share the slides now. Is the slides visible? Hello. Is the slides visible? Okay. Good evening all. Welcome to NPTEL PMRF tutorials of the course Pericyclic Reactions and Organic Photochemistry by Professor S. Shangaraman from IIT Madras. Myself Anisha Suresh, PMRF TF for this course from IIT. So last week, the week 4 modules, mainly the sigmatropic reactions have been discussed. including Claisen rearrangements, Cope rearrangements, 2-3 sigmatropic rearrangements, and 1-3 shift, 1-5 shift and all. So we will be discussing some questions based on those concept. So the major product formed in the following reaction is, so here this is the starting material given. It is treated with KH and diglime at 110 degrees Celsius. So what sort of reaction will be taking place here? Anyone?
8,3 sigmatropic rearrangement.
Yeah. 3-3 sigmatropic rearrangements will be taking place here. And since it is treated with KH now, so here anion will be forming. So it is known as anionic Cope rearrangement. So what will be the product that will be forming? Please try to work out. So for better understanding the stereochemistry, we can redraw it like in this fashion. Okay, this is E alkene here, so it could be drawn like this, and OH will be above, OMe will be below the chair. Now 3-3 sigmatropic rearrangement can take place, so the numbering will be like this: 3, 2, 1, 3, 2, 1. So the shift will be like this. And initially the proton abstraction will be taking place and it will be existing as anion K plus. Okay. So the product will be here OH, and it is coming from this side. Like this hydrogen was above na. So the sorry, this hydroxyl is above na. So this group will be coming from the other side. OMe. Hmm? So this will be the product that is forming. Here the stereochemistry of this alkene will be E with respect to this OMe, and this medial group will be below the plane. So if we will be drawing the final conformation, here tautomerism can take place. This is an enol. It will tautomerize to ketone. So this if we will draw, here this medial group will be below the plane. and this will be the conformation of alkene. It will be an E alkene. Clear? So this is the final product that will be resulted. This 3,3 sigmatropic rearrangement will be taking place in a superficial manner. Hence, stereochemistry will be retained. Will be retained. So this is the answer. Answer 3 will be the correct answer. So anionic oxycope rearrangement is taking place. Anionic oxycope rearrangement is taking place and it will result in the formation of 3 as the final product. Clear? Now coming to the next question. This is question number 2. The structure of the major product in the following reaction is. So here also, what is the reaction that is taking place?
3,3 sigmatropic rearrangement,
Yeah,
anionic coke rearrangement.
yeah. This is also a 3,3 sigmatropic rearrangement. And since this anion is involved, the anion that will be formed from this OH, it is known as anionic cope rearrangement. So what will be the final product that is forming here? Please try to work out. I will give you a couple of minutes. Any answers? Okay, we will try to work out.
Maybe option 4.
Option 4. The right answer will be option 2. We will see how it is coming. Okay.
Okay, ma'am.
So this is the starting material, right? Me, Me, hydroxyl, and this is the other Me. So we can draw it in a chair conformation like this. As is shown here, we can draw it in like chair conformation. So this alkene is E alkene, as you can see here. So we have to draw it in E fashion. And here also the alkene is E, so we have to draw it like this. And this medial group is coming below the plane, and this hydroxyl is coming above the plane. So it should be both equatorial. Now we will carry out the 3 3 sigma tropic rearrangement. So the numbering will be like 3 2 1 3 2 1, and the arrow pushing we can draw like this. Sorry. And it will result in the formation of here Me double bond, Me double bond and OH. So this can tautomerize to give aldehyde, right? Me, and this will tautomerize to give aldehyde. So here this group is this alkene whichever is newly forming, it is E alkene, as you can see here. This is E alkene, and this medial group is coming above the plane, and this medial group is coming below the plane. And if we will redraw it, it can be drawn like this. E, this medial group is below the plane, this medial group is above the plane, and this aldehyde. So here the conformation is R, and here the conformation is S. So according to the answers that we are given, if we are redrawing the structure, then it will be coming like this: E, R, and S. So in the final answer, whichever is given to us, the both medial group will be like beta. Just we are rotating this now. That is why this medial group is coming above the plane. Fine. So the right option will be option 2. So you understood how the stereochemistry is coming, right? We have to draw it in the chair-like conformation, and then do the 3 3 sigma tropic rearrangement. So hence we can assign the stereochemistry for the alkene, either it is E or Z, and those of the chiral medial groups. Fine.
Based on the R and S configuration, we must assign the structure as a linear chain, ma'am.
Yes, yes, yes.
Okay,
Here,
ma'am.
here there is chance for getting mistake when we will draw. So that is why I have shown the R and S configuration, so that while redrawing, it will be easier to understand.
Okay, ma'am. After doing that SAR confirmation, then we must check the configuration of R and S.
Hmm.
Then we must put it in linear and check the R and S configuration.
Yes, yes, yes.
Okay, ma'am. Thank you.
Okay. So the right option will be 2. Now coming to question number 3. So the following reaction proceeds through A. Like 1 3 sigma tropic rearrangement, 2 3 sigma tropic rearrangement, 3 3 sigma tropic rearrangement, or 3 5 sigma tropic rearrangement. So here this is the starting material. It is getting converted into this aldehyde. So what sort of rearrangement is taking place here?
3 3 sigmatropic rearrangement.
Yeah, 3 3 sigmatropic rearrangement is taking place here. So we will see the mechanism of how this is getting converted into this one. So see here, I will draw separately. This is our starting material. So we can give numbering to the carbons like 3, 2, 1, 1, 2, 3. Okay. Then a 3 3 sigmatropic rearrangement will take place. So this carbon will attach to this carbon, this bond will shift here, and this bond will shift here. And if we will draw, it will be like 1, 2, and here the connection will be there. Okay. So it is a 1, 2, 3, 4, 5. Sorry, 3, 4, 5, 6 membered ring that is newly forming. If we redraw it and give the numbering accordingly, 1, 2, 3, 4, 5, 6. In the one carbon, there is an aldehyde, CHO, and in between 4 and 5, there is a double bond, and in 5 carbon, there is one methyl group. Okay, so this will be the final product that is forming. Clear? So since the oxygen atom is involved in the ring which is undergoing this 3 3 sigmatropic rearrangement, it is also known as Claisen rearrangement. Okay, na? So this is how the reaction is taking place. First, we have to number the carbons accordingly for 3 3 sigmatropic rearrangement. So this is 3 2 1, like 3 2 1. Then between carbon 3 and 3, then new bond will be forming. This electron will be shifting like this, and here a new double bond will be forming after breaking of this bond, and it can be drawn in this fashion. And if we count the number of carbons, the newly formed ring is a 6 membered ring. And if we will number it and if we redraw it, then this will be the final structure. Okay.
Okay, ma'am.
Okay. So this is an example of 3 3 sigmatropic rearrangement. Now coming to question number 4. With respect to the following biogenetic conversion of corysmic acid A to 4-hydroxyphenylpyruvic acid C, the correct statement is. So here two-step reaction is taking place. Okay. So here they are asking what is X and Y. So X is Claisen rearrangement, Y is oxidative decarboxylation, X is Fry's rearrangement, Y is oxidative decarboxylation, X is Fry's rearrangement, Y is dehydration, X is Claisen rearrangement, Y is dehydration. So this is the important part that we have to consider, this X, that you will be able to identify, I guess. So see this system. This is a 3, 2, 1, 1, 2, 3. So it can undergo a 3 3 sigmatropic rearrangement, right? And since this oxygen is involved in that system, it is an example of Claisen rearrangement. Hmm? Okay, we will see the mechanism. So you can see here a Claisen rearrangement is taking place. I will draw it separately so it will be easy to understand. So here a methyl group is there. Sorry, this is okay. This was hydroxy probably. So a O H. Hmm. So this is 3, 2, 1, 2, 3. So a 3 3 sigmatropic rearrangement will take place like this, and the resulting product will be here COH will be there, and this will be like CH2 double bond O COOH, and here in between 1 and 2 carbons a double bond will be forming, and we are having this hydroxy, so it will remain as hydroxy. So this will be the first reaction, a 3 3 sigmatropic rearrangement will be taking place. Then oxidation will take place, as you can see here, to give this ketone, and a decarboxylation reaction is taking place. So decarboxylation reaction will be taking place in this fashion, C double bond O OH, and it will give this final product. So the sequence of the reaction is, first a Claisen rearrangement, that is a 3 3 sigmatropic rearrangement is taking place, followed by an oxidative decarboxylation reaction is taking place. First oxidation is taking place, followed by a decarboxylation reaction. Okay. So the right answer will be option 1, that is X is Claisen rearrangement, that is first a Claisen rearrangement will take place resulting in the formation of B. So this will be the B, and after that a oxidative decarboxylation reaction will be taking place resulting in the formation of C. So this is according to whatever we have learned in week 4 modules, this is the important part. X is the important part. So answer will be 1. Any doubts? If there are no doubts, we can move to question number 5. The major product formed in the following reaction is. So what sort of reaction is this? We have seen in the first two questions. So it is also a similar type of reaction. So as you can see, this is a 3, 2, 1, 1, 2, 3. A 3, 3 sigmatropic rearrangement is possible in the system, and since this OH, while after treating with KH, it will result in the formation of an anion. It is known as anionic oxycope rearrangement. Now coming towards the mechanism, as you can see here, first the KH will abstract the proton, resulting in the formation of this O minus. Then this system can be just flipped, and this system is just flipped and shown. So like this. So initially, just this with respect to the center, it is just rotated. So this alkene will be coming to proximity with this alkene. So it can be drawn like this: 3, 2, 1, 3, 2, 1. So a 3, 3 sigmatropic rearrangement will take place, and the resulting ring will be 1, 2, 3, O minus, double bond. This is 1, 2, 3, and 3 will make bond with this, and here a double bond will be there. Then here this enolate, it can tautomerize, resulting in the formation of 1, 2, 1, 2, this system. Okay, so this will be the final product that is forming a six-membered ring, uh, that is bridged with a 1, 2, 3, 4, 5, 6, 7, 8 8-membered ring. Okay, so this is undergoing a 3, 3 sigmatropic or anionic oxycope rearrangement, resulting in the formation of this major product. Any doubts? Option 3 is the right answer. If there are no doubts, we can move to question number 6. Coming to question number 6, the products formed in the following reaction is or are. So here this system is given, it is undergoing a 3, 3 sigmatropic rearrangement, as you can see. 3, 2, 1, 3, 2, 1. It will undergo a 3, 3 sigmatropic rearrangement. So they are asking what is the product that is formed. 1, 2, and 3 options are given. Either 1 only, 2 only, 3 only, or mixture of 1 and 2. So please try to work it out and see what will be the product that is forming. I will give a couple of minutes. You can try it out. Any answers? Okay, we will see. So for this, we have to draw the chair conformation for better understanding. So let me start drawing the chair conformation. Both CH3s are above the plane. So one will be axial and the other will be equatorial. And this is our system. This is our system. It could be drawn like this in chair conformation. Now 3, 2, 1, 3, 2, 1. It can undergo a 3-3 sigmatropic rearrangement resulting in the formation of CH3 like this. Okay. So here the new alkene that is forming is having Z configuration and the other alkene it is having E configuration. Fine. This is cis and this is trans. Okay. Now coming towards the options. So here the both the alkenes are E, E and E. And here both the alkenes are Z. This is the option having one E alkene and one Z alkene. So the only product that will be forming is 3. So option 3 is the right answer. Okay. Is this clear? So The right answer is option 3. Now coming to question number 7. Predict the major product of the following reaction. So this is a name reaction. What is this? What it is called? This is also an example of 3,3 sigmatropic rearrangement. But here, actually, since it is a 1,3 dicarbonyl complex, this will be existing as enol form. So that these two will be hydrogen bonded. So let us see how it is. So this is our starting material, that is beta keto allyl ester. Okay. So this will be existing in this tautomer form, that is OH double bond Me Et Me. Okay. So this is existing in this form, and the name reaction is Carroll Clayson rearrangement. Now what will happen? This can undergo a 3,3 sigmatropic rearrangement. 3, 2, 1, 1, 2, 3. So it will undergo a 3,3 sigmatropic rearrangement, resulting in the formation of E Et double bond Me double bond OH. Okay, this will be the product that is forming. Then it can undergo a decarboxylation reaction like this, resulting in the formation of Me double bond Et. This allyl ketone. Okay. So this question was an example of Carroll-Clayson rearrangement. Now let us see what is Carroll-Clayson rearrangement. So this Carroll-Clayson rearrangement, it is a variation of the Clayson rearrangement. It involves a thermal or base catalyzed rearrangement of allylic alcohols or beta keto esters, and it produces alkenic ketones or decarboxylates. A decarboxylation reaction will take place, resulting in the formation of the final product. So, a beta keto allylic ester, as we have seen in the example, it will undergo a 3,3 sigmatropic shift, resulting in the loss of CO2, and it will produce a gamma delta unsaturated ketone. So, the mechanism will be like this. This is our starting material. It can undergo tautomerization, resulting in the formation of the like this product, resulting in the formation of this conformer, which can undergo a 3,3 sigmatropic rearrangement, as we can see here, resulting in the formation of this compound. Then it will undergo a decarboxylation reaction, resulting in the final product like this. Okay, first this enol will be forming, it can tautomerize to the ketone. Clear? So this was our question. So this is undergoing a 3,3 sigmatropic rearrangement, followed by a decarboxylation reaction, which is also known as Carroll-Clayson rearrangement. And the final product that is forming is option 2, this one. Is there any doubt in the mechanism that we have discussed? If there are no further doubts, we can move to question number 8. The major product that is formed in the following reaction is. So here this is a two-step reaction. As you can see, it is obvious that a 3,3 sigmatropic rearrangement is taking place. And in the second step, in the presence of an acid, an aldol condensation reaction is taking place, giving the final product. So what could be the product? Please try to work it out.
Madam, all these slides are given to us on mail. Are you sent on our mail?
What?
Ma'am, all these slides, whether all these slides will you send
Like
us
it
on our
will
mail?
come like mail, like in the portal, na, there will be one link available. In that you can access. In the Neptel portal, like at the last, you can see one interactive session given. So, in that session, you can take, maybe I will show you that. See here, problem solving session Jan 2025, you can see now. So, in that, if you click on this problem solving session recording, it will give one link. So it will direct to this Excel sheet. There you in this drive you can access the slides, and in these links you can access the YouTube videos.
Okay, ma'am.
Okay. Now coming to this question. So here first a 3,3 sigmatropic rearrangement is taking place like this. 3, 2, 1, 3, 2, 1. 3, 3 sigmatropic shift is taking place, resulting in the formation of this dienol. Then it can undergo tautomerization, resulting in the formation of these two ketones. Then in the presence of H+, that is in H2SO4 condition, this can undergo an aldol reaction. So what is taking place? This will mm, tautomerize in such a fashion like one. I will redraw once. 1, 2, 3, 4. This will be forming an enol again. In the presence of acid, an enol will be formed again, and this ketone will be protonated, and then aldol condensation reaction will result in the formation of 1, 2, 3, 4, 5, a 5-membered ring with a ketone attached next to an OH and methyl group. So this will be the product after aldol reaction. Then condensation will take place, resulting in the, like this will again protonate, resulting in the elimination of this hydroxyl group, and this alpha beta unsaturated ketone will be resulted. So this is the final product that will be forming. Okay. So first A33 sigmatropic reaction followed by aldol condensation reaction. So this is a two-step reaction and the final product will be 4. Is it clear? If there is no doubts, we will move to question number 9. The rearrangement product of the following reaction is. So this is also an example of a 3,3 sigmatropic rearrangement. So the numbering will be like 3, 2, 1, 1, 2, 3. So what is the final product that is forming here?
Three.
Final product will be actually 1. We will see how it is forming. This is 3, 2, 1, 1, 2, 3. So a 3,3 sigmatropic rearrangement will take place. So a bonding will be formed between these carbons, and the resulting product will be like this. 1, 2, this bond will be breaking and a new bond will be forming between these carbons, and here a new double bond will be forming. Okay. So this ring, if we will consider, it is a 1, 2, 3, 4, 5, 6-membered ring, and it is fused with another ring. If we continue numbering, we can number it like 7, 8, 9. And if we will redraw it, first we will draw the 6-membered ring. We will give numbering 1, 2, 3, 4, 5, 6. Between 1 and 6 a bond is there. Then between 5 and 4 a double bond is coming, and connected to 2 is carbon number 9, which is having an oxygen. Then comes 9, 8, 7. Between 8 and 7 a double bond is coming, and 7 and 1 are also connected. So this will be the final product. Okay. Better to number the carbons always so as to avoid confusion. Okay, no? So the right answer is option 1. Now coming to question number 10. Which side chain carbon makes a new bond to the benzene ring upon Claisen rearrangement of the following allylic phenyl ether? So here they have numbered the carbons, right? 1, 2, 3, and 4. So out of which carbon will be making bond with the phenyl ring upon Claisen rearrangement? That is the question. So we can number it like 3, 2, 1, 1, 2, 3. So which carbon will be making bond with the benzene ring? We will see the mechanism. So here a benzene ring is there and it is connected to O CH2 double bond CH3. 3, 2, 1, 1, 2, 3. And if we will give the carbon number, this is C1, C2, C3, C4. Now it can undergo a Claisen rearrangement resulting in the formation of double bond O. So this is carbon number, this is C4, this is C3, C2, C1. Okay. And for regaining aromaticity, this ketone will tautomerize, resulting in the this ketone will tautomerize, resulting in the formation of phenol OH. So the new bond is formed between benzene ring and the carbon 3 of the allyl phenyl ether. Okay. So option C will be the right answer. The bond will be formed between benzene ring and carbon number 3 after Claisen rearrangement of this allylic phenyl ether. Clear? Now coming to question number 11. Which of the unsaturated aldehydes A to D is a sigmatropic rearrangement product obtained by heating of the following ether? Now here a vinyl allyl ether is given and it is undergoing a sigmatropic Claisen rearrangement like 3,3 sigmatropic rearrangement or Claisen rearrangement, resulting in the formation of an aldehyde, unsaturated aldehyde. So what is the like four options have been given and out of which is the right answer or which is the right aldehyde? So let us see the mechanism. So we can draw it in this fashion. Right. Our this was E and then allyl. O. This was our starting material. It can be drawn like this. So then it can undergo A33 sigmatropic rearrangement or Claisen rearrangement. In this fashion, resulting in the formation of this aldehyde. So this is the final aldehyde that will be forming. Okay. Or if we draw it like this, sorry, 1, 2, 3, 4, 5, 6. CH2. This is the unsaturated aldehyde that will be forming. So the correct answer will be option B. Right? Now coming to the 12th question. This is also similar to that of the 10th question. Just we have to identify the product. So we have already solved that question. So let me explain once more. It is an example of 3,3 sigmatropic rearrangement. OCH2 double bond. It is an example of 3,3 sigmatropic rearrangement, and we can draw it like 3, 2, 1, 1, 2, 3. And the final product that will be forming is double bond O, methyl, and a vinyl group. Okay, then it will undergo tautomerization, resulting in the formation of phenol, and this will be the final product. Clear? This is same question like question 10, just they are asking the product. Last time in question 10 they were asking which carbon will be bonding. So the right answer will be option D. Now coming to question number 13. The pericyclic reaction involved in one of the steps of the following reaction sequence is. So this is an example of which sort of rearrangement. Is it a 1,3 sigmatropic shift, 3,3 sigmatropic shift, 1,5 sigmatropic shift, or 2,3 sigmatropic shift? So similar sort of example was discussed in the lecture. So this can be numbered like 3, 2, 1, 1, 2. So this is an example of 2,3 sigmatropic shift. Okay. So what is taking place here? This ylide of sulfur, it will attack at this position. This bond will shift here, and this bond will be breaking, resulting in the formation of this product after 2,3 sigmatropic rearrangement. And in the presence of triethyl phosphate, this will be cleaved, giving the hydroxyl. Okay, so if we have to draw, this is our starting material, SPH O minus plus. So it will undergo a, like we can number like 3, 2, 1, 1, 2, 2, 3 sigmatropic shift. How it is taking place? This will be attacking this bond. Here it will shift, and this positive charge on sulfur will be neutralized, resulting in the formation of, here CH3, CH2 will be coming, O, S, pH. Now this POET thrice, that is triethyl phosphine, it will be removing this SPH and resulting in the formation of OH there. Okay. So the final, like which pericyclic reaction is involved means it is a 2,3 sigmatropic shift. Any doubts? So answer is option number 4. Now coming to question number 14. So here the following reaction involves. So here a diiso compound is given, and it is treated with dirodium tetraacetate. So here the carbon chemistry is getting involved. Okay. So which sort of rearrangement is taking place here? 1,2 sigmatropic rearrangement, 2,3 sigmatropic rearrangement, 3,3 sigmatropic rearrangement, or a CH insertion reaction? Which reaction is taking place here? So this diazo compound, after reacting with this dirodium tetraacetate, it will result in the formation of metal carbenoid, and which will undergo nitrogen extrusion, leading to formation of a carbene. Then what will happen? See, this carbene will be formed. So carbene is electrophilic in nature. So this oxygen lone pairs will add on to this carbene, resulting in the formation of O here plus and a negative charge here. Now this is the substrate that can undergo a 2,3 sigmatropic rearrangement. Okay. Now what is taking place? 3, 2, 1, 1, 2. So it will undergo a 2,3 sigmatropic rearrangement, resulting in the formation of, here oxygen will be neutralized, and this bond between 2 and this carbon and this carbon will be formed, CH2. So this will be the final product that will be forming. An allyl group will be attached over here. The starting material, there was a methyl group, no? Sorry, here there will be a methyl group. That methyl group only is coming here. So okay, that was a mistake. So this methyl group will be remaining as it is. So the right answer for this question is it is undergoing a 2,3 sigma tropic rearrangement. So here a carbene chemistry is getting involved. Clear na? Any doubts? Now coming to the 15th question. So the right answer is option 2. Now coming to 15th question. So this sort of question was discussed in the lecture. How did the allyl group end up here? So here a 3,3 sigma tropic rearrangement will be taking place. 3, 2, 1, 3, 2, sorry, numbering mistaken. 3, 2, 1. Since this position is hindered by this medial groups, no proton elimination is possible to regain the aromaticity. That is why again a Cope rearrangement is taking place apart from this Claisen rearrangement, which will result in the formation of this product. So we will see the mechanism. First, a Claisen rearrangement is taking place between this 3, 2, 1, 3, 2, 1, and it will result in the formation of this product. Now this aromaticity is lost, so it will be unstable. So it can again undergo a 3 sigma tropic rearrangement, 3 2 1, 3 2 1, which will result in the formation of this quinone type system. Then what will happen? A tautomerization can take place, resulting in the formation of this final product. So the allyl either undergoes first a Claisen rearrangement and then a Cope rearrangement, and finally tautomerizes to restore the aromaticity. So the loss of aromaticity might be the driving force for giving this as the final product. Clear? Okay, na? Now coming to the question number 16. Predict the product of the following Claisen rearrangement. So they have already told it is undergoing a Claisen rearrangement. Just we have to draw what is the final product. So it is a 3 2 1 3 2 1 system, and it will undergo a Claisen rearrangement, and the final product forming will be, this will be having carbonyl, and this carbon will be attached here, double bond will be coming here, C3, C2, C1, and this will be attached to the cyclopentane. This will be the final product that is forming. As you can see here, this is undergoing a 3,3 sigma tropic rearrangement or Claisen rearrangement, as oxygen is involved in the system that is undergoing 3,3 sigma tropic rearrangement. It is known as Claisen rearrangement. Then it will result in the formation of this as the final product. Okay. Now coming to question number 17. So this is also an example of Cope rearrangement, that is 3,3 sigma tropic rearrangement. Here the starting material is given and they have mentioned that it is undergoing a Cope rearrangement. What is the product that will be forming here? 3 2 1 3 2 1. it will undergo a co-prearrangement, and the final product that will be forming is, here ethyl will be coming, this bond is breaking, and the phenyl will be attached to this double bond. So this is the final product that is forming in this co-prearrangement. Okay. 3 2 1, 3 2 1 co-prearrangement, or 3 3 sigmatropic rearrangement, and it can result in the formation of this as the final product. This is clear now. Now coming to the next question. Complete the following sequence of reaction and give structures of A, B and C. So here, first this is the starting material. It is treated with KH and it will result in the formation of A. Then under heating condition, it can undergo some rearrangement resulting in the formation of B. And finally, upon treatment with H+, it will give C. Okay. So from this system, it is clear that it will undergo a 3 2 1 1 2 3 3 3 sigmatropic rearrangement. And since this KH is involved, it will result in the formation of O minus, and this is an example of anionic cope rearrangement. Okay. So this will be the mechanism. In the presence of KH, this O minus, like OH proton will be abstracted, result in the formation of O minus K plus. So that is the A. Okay, and then it will be undergoing under thermal condition a 3 3 co-prearrangement. So 3 2 1 1 2 3. So it will undergo a co-prearrangement resulting in the formation of this system. Okay, this bond will be broken, this double bond will shift here, and a bond will be formed between this carbon 3 and this carbon, and this bond will be shifting to this position. So this is the structure of B. Okay. Then upon treatment with H plus, this O minus K plus will be converted into this enol, and this upon tautomerization will result in the formation of this compound C. So this is an example of anionic cope rearrangement. Okay, first proton abstraction will be taking place in the presence of KH, and this anion will be generated. Then it will undergo an anionic cope rearrangement. So this will be the numbering 3 2 1 1 2 3, and a bond will be formed between this 3 and 3. This bond will shift here. This one carbon bond will be breaking, and it will result in the formation of the structure B. And upon protonation H plus treatment, this O minus K plus will be converted into OH, that is an enol, and that will finally undergo a tautomerization reaction resulting in the formation of this ketone C. Clear? You can see the mechanism once again. Proton abstraction, co-prearrangement, then protonation, and finally tautomerization. Now coming to the next question. This is a interesting question. When the terpene Germachrone is distilled under reduced pressure at 165 degrees Celsius. It is transformed to beta aluminone by a co-rearrangement. Give the structure of germachrone including its stereochemistry. So we have been given the product which is formed after the co-rearrangement, and we are asked to find out what is this structure of germachrone. Okay, so how we will find out this? We can draw in chair conformation. This is a trans system. So double bond O, double bond, and here the hydrogen is below the plane, CH3 is above the plane. Methyl will be coming like this. One second. This methyl will be coming like this. Okay. Now it is this is the 3 3 sigmatropic rearrangement undergoing system, and it can be numbered like this: 3 2 1 1 2 3, and it will undergo a 3 3 sigmatropic rearrangement resulting in the formation of, so this CH3 will remain as it is, double bond O, double bond, this hydrogen also remaining as it is, and here a double bond is forming. My pardon my worst drawings. So here a new double bond is forming. Okay, so this is the structure of germanone. This is the structure of germanone. So here this, one second, I will draw little more clearly. This is the hydrogen. So here this alkene is E alkene, sorry, Z alkene. As you can see, this is the higher priority group here, this is the higher priority group here. So this is the Z alkene, this is also a Z alkene. So this is the structure of germachrone. So I have clearly given the structure here. So this germachrone is undergoing a co-rearrangement resulting in the formation of this beta aluminone. Okay, so you can draw the chair conformation for understanding how the stereochemistry of the new alkenes will be defined. Okay, any doubts? I will explain once again. So we have drawn this beta aluminone in this fashion. Okay, 3 3 sigmatropic ring opening sort of mechanism only we are showing here. Both side it is possible now. So here this is the 3 2 1, this is 3 2 1, and this middle is beta, this hydrogen is alpha, and this could be drawn like this. And when we will draw the chair conformation, and when it will undergo a 3 3 sigma tropic rearrangement, this carbon carbon bond is forming and this carbon carbon bond is breaking. And here the newly formed alkene, it is a Z alkene, and this is Z alkene, and this is also a Z alkene. Both the alkenes are Z. As you can see here, this is a Z alkene, this is a Z alkene. This is the structure of germachrone. This will undergo a 3 3 sigmatropic rearrangement, resulting in the formation of beta eliminone. Clear now? Now coming to the last question of today's session, complete the following sequence of reaction and give structures of A, B and C. Here an aldehyde and an alcohol is given, and it is treated under H plus condition. So some reaction will be taking place, and then followed by 2 delta given. So you have to identify A, B and C. So first what will be happening, this alcohol will attack on the aldehyde, resulting in the formation of hemiacetal. As you can see here, the alcohol will be attacking on the aldehyde, resulting in the formation of the hemiacetal, and that hemiacetal can undergo dehydration reaction. So this proton will be abstracted, it will undergo dehydration reaction, resulting in the formation of this product. So this is A. Okay, then as you can see here, this A can be drawn like this: O double bond double bond CH3, and CH2 double bond CH3. Okay, so this is A, and it can undergo a 3 3 sigmatropic rearrangement. See, this is the allyl vinyl ether. So 3 2 1 1 2 3. So under delta condition, it will undergo a Claisen rearrangement, and it will result in the formation of double bond here to methyl, and this aldehyde will be forming. Okay, this is the product that will be forming: aldehyde, double bond CH3 and vinyl. And this can be redrawn like this: aldehyde we can draw like this, Now it will undergo a Cope rearrangement. Here it is undergoing a Claisen rearrangement. Now it can undergo a Cope rearrangement. 3, 2, 1. I will give a different color. 3, 2, 1. 3, 2, 1. 1. Okay. It is undergoing a Cope rearrangement and we are resulting in the formation of this as the final product, which is alpha beta unsaturated aldehyde. It is known as citral. Okay, this is known as citral. So what is happening over here? First, a nucleophilic addition of the alcohol to aldehyde is taking place, resulting in the formation of this hemiacetal, and under H plus condition, it will undergo a dehydration reaction, resulting in the formation of this compound. So this is our compound A. Now the compound A is having a vinyl allyl ether. uh, Compound A is a vinyl allyl ether. It can undergo a 3,3 sigmatropic rearrangement, which is also known as Claisen rearrangement, resulting in the formation of this B. Okay, and this B, when we redraw, you can see it is again a system for Cope rearrangement, and under thermal condition, it will undergo a Cope rearrangement, that is a 3,3 sigmatropic rearrangement, resulting in the formation of this final compound C, citral. Okay, so this is all about the questions based on the 3,3 sigmatropic rearrangements or 2 3 sigmatropic rearrangements that was covered in the week 4 module lectures. So if you are having any doubts regarding any questions that we have discussed today or any of the assignment questions, please feel free to ask. If there are no further doubts, then thank you for attending today's lecture, and you can find the lectures in the uh, link which I have told today. So please watch the lectures in YouTube channel, and if you are having any doubts, you can ask in the comment section of the YouTube channel. Okay, thank you.